So yeah, first of all, thank you to you guys. So as Manager just said, I understand I'm getting between you guys and beer, so I'll keep this brief. So first of all, as I say, Malcolm can't be here today, unfortunately. So if you do see me looking up at the slides and looking bemused, that's probably one of his slides. Just to give you a bit of background, I'm going to talk about sharing data and hiding complexity and how we've managed to do that in Deutsche Bank using Clojure and RDF. So I'm on the graduate scheme at Deutsche Bank. I've been there about a year now. I was first introduced to Clojure about 6 months ago by Malcolm, and then started working for him shortly afterwards. So this is really sort of an experience report on how we found Clojure, how we're solving the big data problems. And when I say solving the big data problems, I mean solving the big data problems, not solving the big data problems. How we can use the patterns and paradigms of Clojure to actually solve these problems. And I'm also going to talk a little bit about the power of graphs as well. So first of all, just to give you a bit of background, I'm working in the risk domain in Deutsche Bank. And of course, like all banks, there's an awful lot of pressures on the banking industry at the moment, not only from the media, but also in terms of financial and regulatory pressures as well. But we've still got the same problems in terms of the data. We've still got the same questions of how we can process data faster. I mean, there's always the requirement to process data faster. So whether it be sort of getting the overnight batch done 50% quicker, moving possibly to even real-time risk if you're coming from the risk department point of view. We've also got data at increased volumes as well. This is particularly true in the risk and P&L area, where the more data we can analyse, the better, the more information we can gather about our risk position, the more accurate figures that we can report. Also, we need to actually report data more precisely. So one of the recent regulations over in the States, the Dodd-Frank regulations, require that we can actually deliver an initial margin call on counterparties. So we need to know our risk position with respect to any given counterparty, so that we know, for example, that we're not exposed to another Lehman's or another Greece or whatever the next one happens to be. So I'd like to introduce you really to Conways Law, first of all. Conways Law is organisations which design systems are constrained to produce designs which are copies of the communication structures of these organisations. So actually, I think that was originally meant as a joke, you know, like one of the Dilbert cartoons, but unfortunately turns out to be quite close to reality as well. Again, quite similar to the Dilbert cartoons. But Conway's Law in action shows that for systems, for example, that are built up organically around these sorts of communication structures, often ends up with quite a lot of quite distinct components to the system, depending on sort of what teams have developed them and what the organisational structure was at that time. The upshot for this, from a technical point of view, is that we sometimes have data flowing through this system via many different protocols, via many different systems, via many different formats. And if we've got Bob trying to send data to Alice here through all of these different mechanisms, how can we be sure that the data Alice gets out at the end is the correct data as put in by Bob at the start? Also, what does it all mean? You've got so many different terms and so many different sort of concepts spread about systems that once you move these different concepts from system to system, you can't really be sure that the meaning has been preserved throughout. And for those of you looking up here thinking I'm about to do some sort of financial rendition of the Elements song, don't worry, I'm not. Tempting that would be, actually. You've got quite a lot of scope for that there. But the thing is here, the data does not typically travel well. And that's one of the problems that we're trying to solve. So the conclusion of all of this is that we need to make our data models span the systems that the data is relevant for. So make sure that the data meaning as you put it in at the start is reflected in the meaning of the data as you get it out at the end. Does this modelling scale, though? If we look at traditional modelling, what tends to happen with it? So as we scale up, obviously we get an increase in complexity. So every new requirement that comes along, every new bit of data that we're required to do, every new report that we're required to produce, the complexity of the overall system increases. The deviations, and by deviations here, what I mean is in terms of the agreed standards, the agreed formats. It's only natural that in a larger system, there's some sort of slight deviations from what you originally intended will come about. And as we scale up, we notice more and more of these. So, for example, I don't know if you remember back from the original slide, we've got at the bottom here, avoiding being blinded by that thing, we've got linkage reference and linkage reference 2. I've got no idea what these two are. I don't know what the difference is, I don't know whether they're formatted differently, and to be honest, I'd be surprised if people in the original system knew either. Also, when we're trying to pull together lots of different concepts into the same system, we tend to have to make the concepts themselves become more abstract. So to make them more powerful, to be able to deal with more and more situations. And of course, when they do become more abstract, it usually means that the understanding that we have of these different abstracting concepts decreases as well. And that, again, that can only introduce bugs. We also actually get a few problems when data escapes its domain model. So data, when confined within a single system, can actually be quite well defined. So the developers know what they're talking about, the business users know the terms that they're using and how they're using them. But as it escapes the domain model, any assumptions that were made about those terms and concepts are lost. Okay, they might well be documented, but more often than not, those assumptions and meanings are lost. And any form of local terms, any form of local variables, don't usually become global ones. It's very difficult to see sort of those terms that we saw on that slide become a globally accepted term for whatever the concept happens to be. So, the implications of this: our primary tool for flexible data processing does not scale. We've got to think of something else. What are we doing to solve it at the moment? Well, at the moment, it seems we're just throwing more code at it. Every new requirement that comes in, every new regulation, we bolt in another component. We put a new component into the system. We're fighting with a code hose pipe, if you like, just firing more and more code at the problem. So I'd like to introduce you to RDF. RDF is a W3C specification that's essentially based around entities, attributes, and values, or triples. And for those of you who've been to Rich Hickey's talk about the database as a value, remember that he actually uses quads, so he puts a transaction in there as well. But for RDF, we just cope with these triples. So the example of this is the cat sat on the mat. We've got a subject, a property, and an object. In RDF, this is represented in what we call n triples format, which I've got an example of down here at the bottom. So for example here, Ginger the cat is sat on the Tech Mesh Hotel's mat. We can also sort of combine together these triples in n triples as well. So if we're still making statements about Ginger, we can say that Ginger is also of type cat. The important thing here is we can also put metadata in RDF. Properties are entities just as much as Ginger is, cat is, mat is. So for example, we can say things about the property sat on. We can say that if we were to represent sat on in a user UI, we could use the string sat on. We can also put in a little documentation comment saying, for example, sat on is the action of sitting on a given object. Granted, for a cat sitting on a mat, you probably don't need it. When you scale up to financial terms, rest assured you do. So what are the features, what are the benefits that we get out of RDF? So first of all, URIs, Uniform Resource Identifiers. These provide globally unique identification and transparency. But the important thing about RDF is, combined with the URIs, we also have namespacing going on, and this allows us to do federated governance. So if I go back here, and I look at the URIs that we have in the RDF model, we're actually namespacing these. We're saying that Ginger is in the namespace of animals.com. So, okay, it's a contrived example. But you can see, for example, if I was to use, for example, a trade source system, could have various properties about a trade, and the trade source system, with the experts that are in there, will have full governance about the terms that are in their namespace. And that to me is the best way. You get the people who are right there in the systems. They know the terms, they know what they mean, they know how to document them properly. RDF is also storage and transfer neutral. When you think about it, at the end of the day, it's just a set of triples. You can just sort of write the triples out to a file as assertions, but we're not worried about whether you sort of store them down in terms of JSON, whatever other format you can name. And transfer them over the wire. There's a couple of sort of ideas about how best to transfer them over the wire, but at the end of the day, we can just transfer them over in pretty much shoehorn them into any format we like. And finally, as I say, the metadata. The metadata is actually very powerful on this and allows you to make assertions about the sort of the quality of the data in the system, the format of the data, and any assumptions that are actually made while designing the system. So a couple of quick observations before we move on. Firstly, RDF has the power to break down silos. So where you have got silos at the moment, for example, between a trade system, between a risk system, between a finance system, RDF has the power to span those silos. So, for example, the triples aren't restricted to being within a particular namespace. I can say, for example, that things in finance are related to things in risk. I can make assertions about properties in the different systems. I can say that, for example, one attribute here is exactly the same as one attribute over here. And I can make assertions and inferences based on those. It's also a very non-disruptive way. RDF can be applied piecemeal, and you start to get the benefits of RDF as soon as you start to apply it. It's not the sort of thing where you have to convert your entire architecture over to RDF to start seeing the benefits. You immediately see the benefits because you get an increase in documentation straight away. You get an increase of more formalized terms and concepts, and you get those benefits straight away. So I'm going to talk a little bit now about how we've actually applied this within DB. We've applied this in a system which we call the RAP, or the Risk Access Point. So within the risk domain, just to set the scene a little bit, within the risk domain we've got what we call the ODS, which is a large data store. Essentially it's a big Oracle box, which houses all of the risk information and sends it off to downstream consumers. But obviously, we don't want all the downstream consumers coming in and doing SQL queries on our database. Right? That'd be crazy. It's a backwards compatibility nightmare. So what we want is a system to get in between those and act as a query buffer, if you like, for the RAP. And it exposes business-level terms rather than SQL tables and columns. We're actually quite fortunate, really, in that the tables in the ODS are all built up from a meta model. You can see I'm talking quite a bit about meta today. Hopefully it's not too meta for this time in the afternoon. The tables in the ODS are all built from a meta model, so that means that we know about all the relationships between entities, attributes, and values. We already have that data. We actually get that in the form of an XML file. RAP actually parses that and turns it into RDF. Why do we go to all of that effort of parsing it and turning it into RDF? Well, first of all, we've got a disambiguation of terms again, as I said previously. So the RAP can actually support multiple data sources as well. So we need to disambiguate. We need to disambiguate between the terms that are coming in from each different data source. For example, one of the early sort of user requirements that we had was to the user wanted to merge the data that they were getting, the risk data they were getting out of the ODS, with some static data that they provided us. And what we could do, by merging these two different data sources, we could treat them as one data source. And this is where we really see the power of RDF as a graph. So if you think about RDF as a graph, the problem of merging graphs is actually quite a simple one, and we get a lot of benefit out of that. I'll come a bit more onto the power of graphs a bit later on. We also get, really for free, this data dictionary, so the documentation. With RDF, because everything's a URI, to get the documentation, the idea is that you grab that URI, pop it in a browser, and hopefully you get something helpful out as a result. I'm not sure how clear this image is. I'm guessing you probably can't see much of it. But the important thing to know here is that we can provide this documentation. Now, at the moment, the URIs that RAP produces are all within the RAP namespace. Unfortunately, the systems upstream don't provide this service. But what the RAP can do is provide this service for them. We can expose their documentation, and so any downstream consumers can take a look at this before they need to make any queries. So it's all very well talking about metadata, and to be honest, there's probably whole presentations you can do on metadata. I'm not going to bore you with that. So essentially, let's talk about actually sort of querying the data and what we can do with it. So, because of the structure of this metadata forming a graph, we thought it was only natural for the format of the query to be just like a query on a graph. Right? That seemed like quite a natural way to query it for us. We allow downstream consumers to create what we call a view. It's quite similar to a SQL view in a lot of ways, which is actually why we called it the view. But here we have a view in graph form. So what this is your typical authors and books query. So what the user is looking for here is to get all of the authors at the top here, And in the views, we allow them attributes and children. Attributes here in the circles, and children here in the squares. Obviously, the top one's not child of anything, it's the root node, right? So this query is essentially saying, get me all of the authors. For all of the authors, I want the surnames. And for each of the authors, I want to get all of their books and their books' titles. Does that kind of make sense? We can actually we can represent this in RDF. Of course, right? That's just a graph. So we can represent that in RDF. And again, here the syntax there's a few little sugars going on here, so I'm not going to dwell on this too much. But essentially, we can say that a view is like a selection where we select the author, we select an attribute. We have also got a child node here, which is book. This is related to it by a relationship, and we want an attribute on the book. So we can turn this quite easily into an RDF form. And we actually merge these in. We actually merge these RDF queries in with the rest of the metadata. And so the queries we can perform on both the view itself and the metadata are viewing, again, they're only viewing one data source. So, using the meta model, the wrap then actually generates the SQL that's required to actually get the results back as and when the view is realized. So the important thing here is that the user doesn't need to worry about the tables, the columns, the joins, whatever. And if you think about it, there's actually quite a few different queries. I mean, if we flip that query upside down, for example, we say, I'm not worried about the authors, I just want all the books, and for each book I want to get its author. That's a different query fundamentally to the first one. But what the wrap does is work out which way the relationship goes, works out which way the join needs to go in the database, and takes away all of those concerns from you. Sorry. So this actually allows consumers to navigate the one-to-many relationships in either direction. So when the results are returned, we then actually start to get some of the benefits of Clojure. Because Clojure is sort of inherently lazy language, it's got support for lazy sequences. The result set we get back from the database is an inherently lazy result set. So this whole process from generating this, well, maybe not generating the SQL, but certainly receiving the results, converting to an intermediate data structure, and then out to whatever format we happen to be required to produce. This is all done lazily. So the advantage of this is that we can pass several gigabytes of data through. I mean, even several tens of gigabytes of data through the wrap, all within the memory of a standard JVM. In fact, the only thing that isn't lazy is this process right down at the bottom, which actually streams it out to the clients. And to be honest, that's the kind of process that says, hey guys, you can't be lazy all day. You know, you've actually got to produce some data. And so that essentially pulls the query through the system. So we've seen a little bit in terms of how we can use RDF to query data in this format, and how the formalism of RDF actually gains us quite a lot in terms of safety and security. I want to talk a little bit now about the power of graphs. So to go over a little bit about an existing pattern in functional languages for traversing graphs and other data structures. And I also want to share with you an idea for how we can combine this existing pattern, but also the views from within the format of the views within the wrap, and come up with an actually really declarative and a really powerful data modeling tool. So it's not just views that we store in RDF in the wrap. We actually store our config there as well. And again, the config forms just as much of a graph as the data itself or the metadata itself. So, for example, we can make some assertions, make some statements about the structure of the wrap infrastructure. So, for example, we've got 3 hosts here, each of which contains an instance. They can actually contain more than one instance, which is why we split them up. We can also make other declarations, like, for example, a host has a host name, an instance has an HTTP web service, which it might well need. The HTTP web service actually needs a port as well. Why do we bother, right? This seems like an awful lot when you can just do it with Java properties files. So we obviously get the benefits of disambiguation in the metadata. I think I've covered that quite enough. I'm not going to bore you with that again. But one of the advantages this does get us is that we can also query the config. So, for example, what I can say about the config is things like, what host am I running on? What sort of services do I need to start up? What ports do I need to start them up on? Who's allowed to administrate these instances? And these all form queries on the config graph. We also get the benefit of actually merging together multiple configuration sources. So within the bank, it's actually very important. I think it's even a regulatory requirement that developers are not allowed access to, for example, production database passwords or any other production secrets or for whatever they happen to be. But what we can do is create two separate config graphs, one that developers are allowed to see and one that they're not, that production support hold. We can merge these two together at runtime and treat them as if they are exactly just the same graph. Right? It just comes back down to that simple graph merging problem. We also sort of disambiguate between sort of static and dynamic config here. What I mean by static config, sort of config that starts up at application startup, but also dynamic config that results as, for example, as like a user administration screen. And we can also combine these two together. As I say, the application using the config doesn't need to care whether it's static config, dynamic config, secret config, doesn't matter. It's all the same source. Actually, that's a slight lie. In the code base, we do actually distinguish between config with passwords and config without, just so that we know to be extra careful in the areas of the system that do have access to the passwords information. So, in functional languages, we actually make quite a lot of use of what we call the zipper pattern. The zipper pattern is a way of traversing data structures in a quite declarative form. Sorry, is that echoing? Are you getting an echo? Or?
It's feedback.
Ah, okay. Just checking. So yeah, we use this zipper pattern to navigate over several different types of data structures. So for example, in Clojure, we get XML zippers. If you think about it, it's actually, the XML zippers are actually quite close to XPath, if any of you ever used XPath. It's quite similar to that. And we use a modification of this zipper pattern which works on graph structures. It's on GitHub, so go and have a look. Feel free to try it out. There's a load of tutorials and everything. So here's an example config graph. Now, I guess you probably can't see very much of this. I'll take you through the bits that we need. Essentially, at the top here, we've got our host. We've got details about the host. We've got production instance. We've got a couple of different services here. One HTTP, one for Swank. Of course, we're working in Clojure, so Swank's actually very useful on this one. And also some information about the JVMs that it needs to start up as well. So things like the memory of the JVM that we need to start up. And all sorts of other configuration data. So, don't worry, you don't need to read all of that. Essentially, we then import the graph into GraphZip. Excuse me, and we do that by importing the RDF triples in form of subject, property, and object. So, if you take my word for it, that's all the data that was in the previous graph, but exposed in triples format. We then need to build up the zipper instance. Now, what the zipper instance is the data structure combined with the node that we're currently visiting. Now, for an XML structure, that's quite easy, right? Because the node that we start off with is obviously going to be the root node. But with a graph, there's no such luxury. I mean, where do you start off when you're traversing a graph? So what we do is we combine the configuration graph with a root node. And in this case, I've chosen this host right up at the top here to start from. We then navigate through the graph. And the way we do this, so can you actually see this at all? Yeah. Okay, excellent. So we then navigate through the graph. We say we want to start off at this zipper. I want to navigate the instance edge. I then want to navigate the service edge, and I want to get all the nodes back. So going up here, I want to navigate the instance edge. I want to navigate all the service edge, and then I want to get all the nodes that are there. So we expect to see the HTTP service and the Swank service. We can also do things like find out the Swank port, and the zipper also allows us to make filters in the query as well. So for example, if I navigate the instance and there's a service, I'm currently at these two nodes. This vector notation here means sort of keep an idea of where you are, but I'm going to take a quick detour in order to filter down the nodes that you're currently holding. So this filter here, for example, says I only want the nodes with type Swank service, which is this one here. So there's Swank, there's the type, there's Swank service. So what we've done there is we've filtered down the nodes to only the ones we actually need in this particular case. When we filtered them down, we come back to the node you were at originally, which is this one here. We then navigate the port, get the node there, and that gives us 4005, the default Swank port. I've actually used zip1 in this case because we know that we're only getting one result back. Everyone following that so far?
How is that related to the zipper pattern?
modifications. That's the purpose of the zipper pattern.
Yeah, that's right. The zipper pattern.
If you're querying, that's useful, no doubt, but I don't see the relation to zippers.
Okay, so the zipper pattern actually takes on two forms in the Clojure API. You're right. That one of the forms is that you can navigate through the graph and make changes to it. When we're querying it, we tend to use this more declarative query syntax. Essentially it's just a sugar put on top of the actual zipper syntax.
Okay, but you don't use the modification part. At least not in this example.
At least not in this example, no. I don't tend to use the modification here. I don't know. Haven't ever found a use case really for it really. So.
Okay. Well, this was introduced by Gerard. Nobody really were exactly for modifications.
Yeah, I'm sure you can, and these zippers work perfectly well on those cases as well. I say we just have another sugar that we can use. So GraphZip actually allows us to merge in, as I said, multiple sources of config as well, and that's quite easy to do from within GraphZip. We've also written, was anyone at Jim Webber's talk yesterday, the Neo4j talk? There's actually a version of GraphZip that's out that can query Neo4j as well. And again, that's up on the GitHub page. If anyone wants to write that one down afterwards, feel free to ask, and I can jot that down for you. So we've seen how we can use sort of the power of graphs to query the config. So now, as I said, I want to share with you an idea where we can combine these two ideas that I've just presented, the idea of having user-defined views and this zipper pattern to create a declarative query language that we can use to define data structures. I'm going to make a bit of a jump here back to XML. So here's the config that I think XML is slightly easier to understand in this context. So here's the config information we had earlier for the host, but this time expressed in XML format. So quite a lot of time, quite a lot of effort, and quite a lot of code, I find, goes into getting input data in some form, so like this. Transforming it into some other data structure and shipping the data structure off to someone else. It seems to be quite a common problem. Without really a common solution. Every time you have to define the transformation that you require. So for example, using the traditional zipper syntax, I find actually one strange thing about the Clojure community. Apparently in the Clojure community you don't say someone's code sucks. You say that it's not idiomatic Clojure. So if this isn't idiomatic Clojure, please accept my apologies for that. So using traditional zipper syntax, what I'm trying to do here is just build up a data structure for the configuration that I can query in whatever way I want, or pass on to wherever I want. So what I have to do, I have to go through all of the hosts. I then have, for each of the hosts, I have to generate a map. So how many people here are familiar with Clojure syntax before I... Okay. Yeah, it's a Lisp, it's allowed to have brackets, right? It's AST, right? Yeah, essentially. Essentially, yes. So the braces here denote a map, which is just essentially a key-value map. The square brackets here are vectors, and what else? Well, I think that's all we've got there, really. And braces are usually function application. Sorry, brackets are usually function application. So here we're generating a map, host name and instances. And for each of the maps, we then need to do a sub-query. We then need to do another query on that XML. Admittedly, we can start off from like where we were at the host node. But again, we need to do a query. Instances. For each instance, I want another map. Then for each service, I want another map. And for every part in the data structure, it goes on. And the more complicated the data structure, the more of this you've got to write. I mean, it doesn't get any better, really, when you're using data log syntax. Right? Data log makes your job a little bit harder, because Datalog's queries only really return flattened rows. You know, it's almost like the 90s, and we're going back to relational databases again. Come on, guys, we deal with data structures now. We're in Clojure. So, using the Datalog syntax, for every level, I need to make a Datalog query. So I need to make a query for each of the hosts. I need to use the outcome of that to define what the instances are. And I need to use the outcome of the instances to do another query on the services if I want any form of nested data structure. Of course, I could return flattened rows, but it's much easier to query a nested data structure than it is to query flattened rows. So, to step back for a moment. Oh, where's that gone? Okay, so to step back a moment, we can actually use the idea of having the Clojure zippers as metadata for the data structure that you want to come back. So we're using I'll say that again. We're using Clojure zippers as metadata for the data structure that we want. I want you to imagine now. So hopefully you've got a rough idea of the sort of data structure I'm trying to get out of this. I'm trying to tease out of all of this code. Right? I just literally want a Clojure data structure of a representation of the input data. So imagine how you would actually sort of convey that to a fellow developer. How would you tell them how to transform that code? If it was possible to write that transformation as a description of the transformation rather than a description of the algorithm that you have to go through, this code would be a lot more understandable. So the main idea of this change is to introduce a map construct into the zipper syntax. And this will allow data transformations such as these that we write every day to be transformed into a more declarative syntax, saying exactly what you want rather than how you want it. So the enhanced zipper query would look like this. Let me just run you through it. So what I'm saying is that I want a data structure here, which starts off at the root, goes down all of the hosts, and then I define the data structure that I want. I want a map. In the map, I want a host name. How do I get the host name? Well, I query it using this little query here. And you can see how much of the boilerplate has been taken away by this little syntactic sugar. This caret :1 here, incidentally, is just a little bit of Clojure metadata saying that there's only one host name for any given host. So that way we don't have a list of one element, we just have the element itself. Likewise, for instances, what's the query for instance? To get the instances part of the map. Well, I go down instances, I go down instance, and then I want another map. Here I'm defining exactly the data structure that I want back. I then say each instance has an instance name. How do I get that? Well, here's a query for that. Each of the services, again. So what I'm saying here is exactly the format of the data structure I want back. Everyone following that? Have we? Brilliant. Okay, so the result of that is then this data structure, which actually in Clojure looks remarkably quite terse. And now the possibilities with this is that you can query it using any of your standard Clojure core functions. So just get in or whatever else it happens to be. It's just like the same as traversing a normal Clojure data structure. You don't have to worry about all of the boilerplate going through of working out which queries, how to flatten it, how to unflatten it when you get it back, any of that. So, on that bombshell, I'm going to sum up. Essentially, what we've shown is that we can use RDF to really disambiguate the data we have. We can use software like the wrap to be able to query databases using this RDF, and we've seen how the power of graph can really lead to a good declarative syntax for this data transformations, which we do every day. Thank you very much. I'm happy to take questions. So was that the queries that are natively stored as RDF, or?
No, the actual triple itself. Was the triple stored as RDF within the database, or were they stored as?
No, it's just a normal relational database, normal Oracle box.
When you talk about the views and the queries, were you using like your own querying syntax, or? I think there's something like Sparkle for querying RDF triples. So was that some form of the Sparkle query syntax, or was it something your?
We did actually originally go for Sparkle, because it is actually a very good sort of query language for graphs. But again, it comes back with this problem that it only returns flattened rows.
I thought there's a way to build a return graph with Sparkle.
I haven't. Okay. If that's the case, then I haven't.
Used it. I just read the specification, so maybe that's just specification.
Right. Okay. But to be honest, if we did, okay, but if we did that, I mean, we don't have any Sparkle endpoints at the moment. So to be honest,
if you have it in normal database, then
yeah. I mean, I'm sure if we could use a SPARQL data point for that sort of query, then it would probably provide some advantages. But
Thanks.
The graph set that I really wrote,
Mhm.
does it support weighted graphs and that sort of stuff?
So does it support?
Does it support weighted graphs where you can find shortest path and that sort of stuff?
It doesn't at the moment. I'd say it's only been a spare time hobby project of mine. So, I mean, it's a good idea, and it's probably something I'd look to extend it with. I'd say if you can fork it on GitHub and provide it, I'm sure I'd be happy to take that one on. Would you like the addresses for that again? Where was that in the presentation? There it is.
Hi, first, great work for the RDF and Clojure. I guess, I mean, like a ton of questions on also pointers. Zipper is a graph with the pointer. It's called a pointed graph in RDF. I mean,
Okay.
it's already a time for that. It's like a graph when you have a start node so it's called a pointed graph.
Oh, okay. Thank you.
Second, how do you do term governance? Since in the RDF, anybody assumes anything. I mean, how do you manage security of term and stuff like that?
We don't, to be honest. The only thing we could do with that is to apply to actually turn them into a quad, and then have the last one as the governance of the assertion. So to say that, for example, this particular person made that assertion at this time, and you can then combine that and say, for example, how much do I trust that person making that assertion at this particular time? In terms of security, we don't actually make those assertions. I say at the moment it's really only an experimental prototype at the moment. We're only drawing down data from one system at the moment. But I'm sure that if the need arose, then we could actually include that form of security.
Did you have any plan to use ontologies, better ontology that we use currently to describe your format? For example, in your query, I saw cardinality fixed, like the one when you project on this over the same element. In OWL, you can fix cardinalities, and since you are using Clojure, I mean a dynamic language, you can first scan the ontology and then project.
Yeah, and again, we certainly could. We did actually prototype that a while back, but what we did find that the cardinalities were actually included in the metadata that we were being passed in. So the cardinalities were all on that side rather than on the actual query side. The query itself doesn't need to worry about the cardinalities. You know, I mean, if we've got one author having multiple books, then the metadata already knows what the cardinality is. And in that, I believe we do actually use the OWL ontologies for the cardinality. Okay, there's no further questions. So yeah, thank you very much.